Composition of functions. When you see this word composition, think of the word composed as in composed of, because we're talking about parts. We're talking about taking like two or even more functions as like parts and putting the parts together to make a new function that is more useful to us. So it's like building functions, building newer functions from older functions, or big functions from little functions, or something like that. We're building new functions. Now, when would you want to do that? Well, here's a nice example. Let's say you spring a leak. You're on an oil rig somewhere out in the ocean or whatever, and all of a sudden you spring a leak. So we'll just assume that the oil slick is going to grow as a nice circle. Now, of course, if there's an ocean current or something, it'll probably go like that. But let's just, to keep it easy, to keep that our first example easy, we'll just say, no ocean currents, no wind, nothing fancy. It's just a circle. If you want to add that complication later, you can, but for now, it's a circle. So anyway, the oil rate the oil slick is growing in a circular shape, and this is a good assumption. It's growing at a constant rate of 10 square meters per minute. The area expands at a constant or steady rate. Why is that a good assumption? Well, if the volume flow rate is steady, which is just saying it's leaking at a steady rate, bubble, 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 bubble. It's just leaking at a steady rate. Well, that would tell you that the volume expands at a constant rate, wouldn't it? Not the area, but the volume. So why are we saying that the area expands at a constant rate? And the reason is because with these oil slicks, there's the surface of the ocean. The oil slick actually just keeps an extremely thin constant thickness. And so because the thickness is always the same, to add volume, you basically have to add area. It's a constant thickness, and actually that thickness is amazingly small. You should look it up on Google. I looked it up once, and I can't remember what it was, but it was like 0.0 something. It's amazingly small. But anyway, because it's a constant thickness, the area will expand at a constant rate. Okay, so that's kind of our assumption here. So because it's a constant leakage rate, constant gallons per minute or whatever, and because the thickness is going to always be the same, the area is going to be expanding steadily at a constant rate. Okay, so let's say an hour goes by or whatever, and so now it's a little bit bigger. So this is 1 hour. 1 hour of flow. Okay, cool. Now what happens when another hour goes by? Well, you're going to add the same area. But notice that does not mean you're going to add the same thickness ring. That can't be true, because imagine if you kept doing that and you got all the way out to here, you're starting to add some really huge rings, and they're going to have really huge areas. But you're supposed to be having, every minute or hour or whatever that goes by, you're supposed to always add the same area every time. So because the circle has grown, this next level, and I'm exaggerating, I think I'm exaggerating, I might not be, but anyway, this is in here, this is another hour of flow. So what I'm getting at is that here's the radius, right? So the radius grows, but then it grows not quite as fast, and it grows not quite as fast. And so the radius expands, how should I say, at a slowing rate? I guess that'll work. So even though the area is expanding steadily, constant rate, the radius is not going to do that. The radius is going to keep expanding, but it's going to keep expanding more and more slowly. So let me get these words out of the way here. And you might just think of blowing up bubble gum or something. Here's Harry. He's got a mouth. He's blowing up some bubble gum. When you first start to blow it up, it goes, it gets big fast, right? But then if you blow at a steady rate, you know that the bubble is going to start growing more and more slowly, right? It's the same effect. It's the bubble gum effect. And if you're not picturing that, go get some bubble gum. Figure it out. Blow a bubble. You'll see. Anyway, that's what we got going on. So The reason we might be more interested in the radius than the area is because radius that's like distance from the spill here, right, from the oil rig or whatever. Well, if you're wondering when are we going to hit this city, you're more interested in the radius of the slick than you are the area of the slick, right? So you need to figure out, when's it going to hit the city? Well, I better get an expression for the radius in terms of time, and that's exactly what the question is. So the question, looking back at the question, the area expands at a constant rate, 10 square meters per minute. Write an expression for how the radius changes with time. And again, neglect ocean currents and all that stuff. Hey, look at those nice straight lines. I'm impressed. Anywho. So we need to play with some functions here. Now, we can build a function for area from what they're saying here. It's increasing at a steady rate. Now, whenever you hear that term steady rate, that basically tells you straight line equation. So think in terms of, we'll say we start at 0. We'll just, we'll start the clock running as soon as they spring the leak there. It starts at 0 and then it keeps climbing, right? And it climbs at a steady rate. 10 square meters every minute. 10 square meters times the number of minutes. You can make a graph and dig it, because this is time going by. This is area, right? You start at 0, that's your y-intercept. And then every 1 minute, the area goes up 10. Over 1, up 10. Over 1, up 10. That's a slope. This is like an mx plus b thing, where b is 0 and m is 10. It's the same thing. Anyway, there's our nice function for area. That was cool. How are we going to get at the radius? Well, it's a circle. I know area and radius are related by this equation, right? A equals pi r squared. So let's rearrange that. Let's maybe I'll just turn it around first. Pi r squared equals a. I want the r on the left, right? So r squared is equal to a over pi. Okay, take the square root of both sides. Now usually when you take a square root, you're going to put a plus or minus in front. That's actually very important to remember. When you take a square root of both sides, you have to put a plus or minus in front. Why? Because this symbol doesn't mean plus or minus. This symbol just means the positive root or the principal root. So if you actually want both square roots, you have to say it by putting the plus or minus in front. So after belaboring that point, we're not going to put a plus or minus. Why not? Because who cares about negative radiuses? They have no physical meaning in this problem. Negative radius? What? There's no negative radius here. So after all that, all we're going to do is this. Okay, so notice I've got a nice function for r that has an a in it. And then up here, I have a nice function for a that has a t in it. Well, these two functions got to get together, don't they? So what we do is we say, well, basically, area is equal to 10t. Just make the replacement there. So r is equal to the square root of, not a, put the 10t in. I don't have to worry about the 0, right? Put the 10t in over pi. Let's make that look a little nicer. Let's make that look a little nicer. There she blows. That'll be our answer right there. So now you've got a nice equation for how the radius varies with time. And by the way, always think of your graphs, right? This is a square root of t. Remember how square root functions look like when you graph them? They kind of go over. They're like a hook shape, right? Which shows you that as time keeps going by, the radius, yes, it does keep growing, but more and more slowly, just like we were expecting. It's the bubblegum effect. Okay, you just did a composition of functions, whether you knew it or not. That was composing functions, just putting them together. Put the r function and the a function together to build a new function. Basically, r is a function of a is a function of t, so now r is a function of t. Okay, it's a new function. Now, we have to look at this a couple different ways just because, well, notation. We got to get used to some notation here. So we're not going to solve the problem over, I promise. We're just going to incorporate some function notation into what we just did. So what we just did was, let's see, we took this r function And now that I'm using function notation, notice r is a function of a. You plug an a in. So r is a function of a, and it looks like this. There, is this looking more, sophisticated or whatever? This is what we're doing. Oop, now I need blue. Then we had this other function, a, which you plug in time. So a is a function of time. And it was basically 10 times the time. Okay, those are the two functions we played with. And then what we did is we literally took this 10t and we plugged it into that formula in place of the a, right? That's what we did. There's a slightly new way of saying it. You could say that we took this a of t and we plugged it into the r of a. Notice it's the same thing. It means the same thing, right? But we say it this way. R composed with a. And the order is important. This is not a composed with r. This is r composed with a. Just the way you look at it. R composed with a. Okay? Same order that you read it in. R composed with a. That's how you say it. That's how you speak it. If you might see a question that says find r composed with a, and that's all they mean. You might see it written this way. This is actually my favorite way to write it. That means r composed with a. And to me, that's the most intuitive, because I had r of, and then I took the a of t and plugged it in there to get r of a of t. Just like this, right? To me, that's the most natural notation. But there's another one that's very important. You have to know what this means. It's r with a little open circle of a. Okay, r with a little open circle of a. So this is called a composition symbol, I guess. And what's important to keep in mind is it does not mean multiply. I'd be rich if I had $1 every time I asked somebody this question and what they did was multiply. Should you get partial credit if you multiplied? No, you shouldn't get partial credit if you multiply, because that's not what the symbol means. You have to know what the symbol means. That little symbol means r composed with a. So again, this and this and this, they all mean exactly the same thing. And one more thing, you might sometimes see it written this way, which is just trying to emphasize that this composition here is a function of t. That's why they're putting this here. That this composition, you have to group it, the composition is a function of time. So it all means the same stuff. Let's see, is that all I needed to say? That's all I needed to say there. And it's called a composition of functions, I guess. Okay, and now I need to show you another thing, and that's what does this look like when you're playing with math books. When you're playing with math books, go away. Okay, when you're playing with a math book, they're not so much going to give you a function r of a. What was r of a? R of a was this function, right? They're not going to give you that so much as this. They're going to call it, they call everything an f of x. And every input is an x, and every function is an f of x, right? Pretty much. That's what they'll call it in a math book. And then they're going to say not so much a of t, which we had just 10t. They're going to call it, well, it's a different function, so they have to call it something else, so they call it g of x. And they call it 10x. And this will throw you, because it's like, well, wait a minute, you're using an x here and you're using an x here? That's not the way it was over here. We had an a for an input, we had a t for an input, but over here, x is always the input. What's going on here? So it's just the math booky condensed version of every input is called x and whatever. And then, I guess I'll go to purple now. Not so much. They're not really going to say r composed with a. They're going to say f composed with g. I should make that look a little more clear. F composed with g, i.e. plug g of x into f of x, i.e. you're going to plug this in there, and you're going to get, well, guess what? The x becomes a 10x. See, everything's a function of x in these math books. They're weird like that. But anyway, so I want to point this out and be very clear about this, because when you're working math book examples, sometimes it's very easy to lose sight of what's really happening. It's like, what do we have all these x's for? What's x's? In the background, there's probably something that's happening. There's an oil slick with an area that changes with time and a radius that changes with area, blah, 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 blah. Okay, so that's kind of an FYI is what that is. Just don't let all these f of x, g of x things blind you to the reality that composing functions, all it is plugging one function into another. That's all it is. That's all it is. So, maybe I can do this problem a little more quickly. I had to introduce a lot of ideas with that previous one. But this ability to use formulas to build as building blocks, to build better formulas. How should I say this? It's exciting. Once you pick this skill up, it gets to be pretty exciting because you can start to analyze the world around you and be happy. It's kind of cool. So we'll do one more of these sort of, I'm calling it real life example. Godzilla, the real Godzilla, is stepping on a cylindrical chunk of Play-Doh that initially measures 20 inches tall with a 4-inch radius. Okay, so I'm going to draw a cylindrical shape of Play-Doh. Here we go. Not necessarily to scale, but you get the idea. It's like a soup can type shape. It measures 20 inches tall. Okay, that would be this dimension basically, 20 inches up. And if you want, you can draw his foot up here. I'm not going to draw his foot. But it's 20 inches up here, and then since it's a cylinder, you would draw one of these center lines down it, and then you could say that the radius is measured from the center line out to here, and the radius here is 4 inches. So that's our initial dimensions of this can. Okay, cool. Now he steps on it. And he steps on it slowly. This is not just a big stomp. He steps on it kind of squishing it slowly. Assume the Play-Doh retains a cylindrical shape as it deforms. Retains a cylindrical shape. How's it supposed to do that? Doesn't have to deform. Such that its radius is going up while its height is going down. So in other words, the can is going to get, I don't know how to draw this here. Let's assume the can stays on the ground here, but it's going to get wider as it gets shorter. See what I mean? So it's going to do something like that. So maybe I'll put the arrow over here someplace. So the height, and maybe I'll label it out here, is going to be some function of time. Draw my center line here, and then the radius is going to be some function of time as well. So the idea is, as this gets squished down, the radius gets squished out. So you end up with a shorter, fatter cylinder, shorter, fatter soup can type shape. Okay, that's what we're going to say. Now, that's not a bad assumption. Probably not a great assumption. It's probably going to bulge a little bit, right? Whoops. Probably going to bulge a little bit, but we won't worry about that. We're just trying to get some basic idea of how the radius is going to change with time. So, and that's the question, how does the radius change with time? If, now we're given this information, the height is decreasing steadily. Remember that whole straight line stuff? Steadily, decreases steadily. It's a straight line stuff. So, let's see. Let's try to write that down here. Let's write that right now. The height is decreasing steadily at 1 inch per second. So time is the variable, is the input here. You plug in a time to figure out how tall it is. So h is going to be a function of t. We're starting not at 0 this time like the oil slick. We're starting at 20 inches, right? That's our initial height. And then we're decreasing, which is like a negative slope. And what's our rate? Our rate is 1 inch per second. So that's like a slope of 1 inch per second. So you don't have to say 1t, you can just say t. If you were to, so actually we figured that out just by reading their statement. That's pretty cool. So what would that look like? When t is equal to 0, you're at a height of 20, and it's going down with a slope of -1. Notice there's going to be a point where the height is 0, and we're not gonna have negative heights. Let's not think about negative heights. But anyway, that's the idea. It's just the height is going to be decreasing steadily according to that little equation, that little function right there. Cool. How does the radius vary with time? That's the big question. So after we're done taking all the information up here and sort of saying, oh, that tells me this, that tells me this, that tells me this, now it's up to us to figure out how do I get at the radius. To get at the radius, you probably want to, well, I think I might have skipped over that part, did I? Yeah, I guess I'm not saying it outright, but we're going to assume, so since they didn't say it, we'll say it, assume the volume remains constant. I mean, the Play-Doh has to stay there, right? I suppose what we're trying to say is it's incompressible Play-Doh. It's not going to get... it's incompressible in the sense that it keeps the same volume. It's like water. You know, if you take water and you play around with water, you'll find that if you push down here, it's going to push up somewhere else, right? If you push in here, it's going to push out somewhere else. That's the problem with water. You can't just squish water. Try squishing water. Try taking a gallon of water and making it smaller. You won't be able to. That's what I mean by the incompressible. So assume the volume remains constant, and by doing that, see, I know what the volume is of a cylinder. It's pi r squared h. You could look that up if you didn't know it, but pi r squared h. So what's the initial volume? It would be pi. The initial r was 4, and the initial h was 20. And so the initial volume was, that's a 16 times 2, that's a 320 times pi. That's the volume. And if that's going to get constant, well, see right here, I've got a nice formula that relates volume to r and h, and I'm saying the volume's going to stay constant. So that means that this pi r squared h is going to always be 320 pi. And while we're at it, we'll cancel the pi's. So it's saying that r squared h is always going to be 320. It's going to stay the same the whole time. This, you might be thinking, is an inverse variation type relationship. H varies inversely with the square of radius, you know, whatever. Something like that. So this is getting useful. We're after the radius, so let's solve for radius while we're here. So that's going to be a 320 over h. And so r squared, or excuse me, not r squared, it's taking the square roots of both sides. R is going to be the square root of 320 over h. Okay, cool. And now we can rock and roll. We can take this formula up here for h, and we can plug it in, and that result will be called r composed with h, which I can write this way. Or I can write this way with an open circle, but I don't want to. So r composed with h of t is, dun, 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 got a square root, we got a 320 on top, and we've got the h on the bottom, and the h is this 20 minus t thing. There she blows. I invite you to plug in some points for t and make a graph. I think what you'll see is that the radius is it's going something like this. It's going woo. It's same thing, but incorporating function notation. Well, I already kind of did right there, but what we would do is we would do something like this. We would say h of t is 20 minus t. R of h is square root of 320 over h. And from there, r composed with h is r of h of t is equal to that same result, 320 over 20 minus t. So there's nothing different there. Nothing different there. The math book version would look like this. Instead of r of h equal the square root of 320 over h, we would have f of x equals the square root of 320 over x. Instead of h of t is equal to 20 minus t, they would give us g of x is equal to 20 minus x always with the x. And then instead of r composed with h, they would ask for f composed with g. And you would get, when you plug this into here, you would get square root of 320 on the top, and you'd have the x becomes a 20 minus x. I think that's the part that freaks people out the most. Take x and turn it into a 20 minus x. It's like, how can you do that? Well, it's because we're talking about inputs to functions. You can input whatever you want. You can take the x and plug in a different version of the x, like a 20 minus x is like a different version, so to speak. So yeah, this you can do it. So that's the math book version. Okay, well, I hope you're kind of enjoying these. This is what the math is for, really, in terms of real-world approaches and stuff. Tech applications, engineering applications, science applications. It's cool stuff. Okay, so I need to show you something else, and we'll just switch back into pure math book mode. It's going to be f of x's and g of x's, no more Godzillas. But I need to talk about domains here, especially if I can erase. Okay, need to talk about domains here. So, compose f with g and state its domain. So composing f with g means this. It means this. What it means is that f with g. The g gets plugged into the f. See what I'm saying? The g gets plugged into the f. This is the g function. You plug it in to the f function. So wherever you see an x over here, that's where you're supposed to put your input, and that's going to be your input. So this is going to be a little bit on the hairy side. So we've got f composed with g is. So I see an x. In its place, I'm putting x minus 1 over x plus 1. Underneath, I see a 2, and I see an x. So where I see the x, I'm putting in an x minus 1 over an x plus 1 minus 1. Well, we just got to simplify that carefully. So I've got an x minus 1 there, I got an x plus 1 there. Just leave the top alone for now. Let's simplify the bottom. Now you want to think of that 2 as a 2 over 1, right? Whenever you're doing fraction type stuff, whole numbers are like over 1. This 1 here is like a 1 over 1, but more importantly, we're going to have a denominator of x plus 1 here. We're going to have two things down here. They need to have the same denominator before we'll be able to combine them. So I'm setting myself up to do some common denominator subtraction stuff. So what do we got here? The top is the same for now. The bottom is a little bit bigger. I'm going to do the distribute thing here. So I've got a 2x minus a 2 over an x plus 1 minus, and then this fraction is just going to be an x plus 1 over an x plus 1. Okay, be very careful with this next step. Both fractions have the same denominator, so you know you're going to be able to just add right across the top, right? Or subtract right across the top. You need to look at this as in parentheses. This is going to be a minus x. This is going to be a minus 1. So I've got a 2x minus an x is an x. I've got a negative 2 minus a 1 is a negative 3. Make sure you agree with me. So it's a 2x minus an x is an x. It's a minus 2 minus a 1 is a minus 3. Okay? Hey, make sure you match that. Now, to unstack a fraction, you do the top divided by the bottom, which means you do the top times the reciprocal of the bottom. Right? That's how you divide fractions. Top, you know, if I had 5 over 10, I would do 5 divided by, well, let's do it this way. If I had 10 over 5, I would do 10 divided by 5 is 2, right? Fractions just mean division problems. And how do you divide fractions? You multiply by the reciprocal of the second fraction, right? So that's what's happening here. So I've got the top, there's the top, x minus 1 over x plus 1 times the reciprocal of the bottom, so that'll be an x plus 1 over x minus 3. Okay, and now an important point. Before you cancel anything, check for domain restrictions, which basically means division by 0 type stuff. Check for domain restrictions. So you look at this denominator and you say, well, x cannot be 3. And then you look at this denominator and you say, well, x cannot be negative 1. Okay, so you note your domain Why did I erase that? You note your domain restrictions, then you can cancel. So then you cancel the x plus 1s. So the reason it's important to check now is because, you know, you might lose track of this x plus 1 and sort of forget about this domain restriction here. So before you cancel, you do that. Now that's the only thing that cancels here. So here's our answer. I guess I'll go back to blue. Right. So f composed with g is, that's what we were doing, right? F composed with g is, we get this x minus 1 over this x minus 3. And you can tell by looking at your answer, x cannot equal 3. But like I say, you have to check before you cancel anything. We also have to remember that x cannot be negative 1. There's going to be a hole in this function at x equals negative 1. This is going to be a vertical asymptote. Remember, if the denominator is 0, it's a vertical asymptote. But this, since it's sort of like it would have been a vertical asymptote, except it canceled. That's called a hole. You can get a hole in your graph. Anywho, now to write the domain. See, here's the thing. Those are not the domain. Those are restrictions from the domain. In other words, the domain does not have 3 or negative 1. So what does the domain have? And here's a nice notation for you. The set of all real numbers x with the following conditions. What conditions? Don't use 3, or actually don't use negative 1, and don't use 3. Put these in order from least to greatest. Same as the number line, right? Number line goes from negative infinity to positive infinity. You list them in the order that they're showing up on the number line, left to right. So please do that always. So anyway, that would be a nice way to state your domain. It's not what numbers is it not. The domain is all the numbers that are accepted. What are all the acceptable inputs? The set of all acceptable inputs is the domain. And so it's the set of all real numbers except these two. Now if you want to do it with that interval notation, again, go in the same sense as the number line. The number line starts at negative infinity, goes to positive infinity. We don't have this and we don't have this. So it's like we got two holes or something in our domain. So how would you write that? You would say, well, I have an interval that goes from negative infinity to negative 1, not including negative 1. And then I've got another one, so union symbol. Now I've got a thing in here. I can go from negative 1 up to 3. Again, not including 3, round parentheses. And we've got one more chunk, so union symbol again, the other side of 3 to infinity. So that's how you would do it with the interval notation. Okay, let's do one more example of this. So good fraction practice here. But also, here's something to keep in mind here. This is saying compose G with F. Notice they kind of said it backwards. Before they said F with G. Here we're composing G with F. We're composing G with F means we're actually plugging F into G. F gets plugged into G. Here's my f of x. I go plug that into the g function. Now the g function, where does it take inputs? It takes inputs there. It takes inputs there. So where you see the x's over here, you replace them with this as an input. Okay. So what's that going to look like? Oh, it's going to look like a mess. So make sure you go in the right order. By the way, you could also do things like f composed with itself, g composed with itself. You would have to take the function and plug it into itself, which is kind of fun, but you can do it. Anyway, g composed with f. So I've got 3 times, I'm over here, 3 times the input. But the input is this whole thing. 4 minus x over 3 minus 2x. And then I've got this minus 1. On the bottom, I got 3 minus 2 times the input. Okay, yeah, That's like, what do they call it? Mighty dog? Mighty dog, dog food or something? This is meaty. You can chew on it, that's what I'm trying to say. So let's see now here. Let's be very careful now. Remember, whole numbers are like over 1. When you're starting to do fraction action, think of a whole number as an over 1 deal. So that's kind of what the first part looks like when you clean it up. Minus, now that's 1 is like 1 over 1, but the point is we need to have a common denominator of 3 minus 2x, so you have to multiply top and bottom by 3 minus 2x. That's setting up the top. Setting up the bottom, this 3 is like a 3 over 1, and we're going to need to have a common denominator of 3 minus 2x over here as well. So I'm going to have a 3 minus 2x over a 3 minus 2x. Good. Minus. And again, think of this as a 2 over 1, multiplying a 4 minus x on the top, and a 3 minus 2x on the bottom. It's kind of a lot of writing, but you can see what's going on here, right? So now what I want to do is, see, we have a common denominator here. And because we have a common denominator, it means I can start combining across the top. So if I read across the top, what am I looking at? Across the top, I'm looking at 3 times a 4 minus x minus parentheses 3 minus 2x. Don't lose these parentheses. They are real. They are right there. They are real. So that's on top, and that's all over a 3 minus 2x. Nice big fraction bar here. Come to the bottom. Similar kind of deal. We have common denominators now, 3 minus 2x, so subtracting across the top. 3 times a 3 minus 2x minus a 2 times a 4 minus x, and that's all over 3 minus 2x. So what is this turning into? This is a 12 minus a 3x minus a 3 plus a 6x. All over that 3 minus 2x. And that's all over 9 minus 6x. And this is a minus 8 plus a 2x. All over 3 minus 2x. Let's come down here now. So cleaning this stuff up, we got to see. I think I'll do the x's first. A negative 3x and a plus 6x makes a positive 3x, and a 12 minus 3 makes a 9. Okay, cool. Over a 3 minus 2x, and then make this the big fraction bar. And on the bottom here, I've got a, let's see, I've got a negative 6x plus a 2x is a negative 4x, and I've got a 9 minus 8 is a plus 1 all over 3 minus 2x. So remember, we're going to do top times the reciprocal of the bottom. That's to cut to the chase. Top times reciprocal of bottom. Again, it's this divided by this, but the way you divide a fraction is to multiply by the reciprocal. So here's the top. 3x plus 9 over 3 minus 2x. And then let's flip the bottom over. 3 minus 2x over, and instead of negative 4x plus 1, I think I'd rather make that look like a 1 minus 4x. That looks pretty good. That looks better, doesn't it? Yeah, I think so. So anyway, this is the part where I say again, before canceling, before you cancel anything, check for domain restrictions. Look for division by 0 problems. You obviously have a problem here. You cannot put in x equals 1/4. Either you see that, or you can go like this. Set this equal to 0. Subtract 1 on both sides. Divide both sides by negative 4. A negative 1 over a negative 4 is the same as a positive 1 over 4. And then also, looking over at this denominator, we cannot have a 3/2 for the same reason. Take 3 minus 2x, set it equal to 0, and solve. You're going to get x cannot be 3/2. Okay, so now we can cancel. And so now I will cancel. Gone. And so what do we got here? We've got f compose. Nope, this was the opposite. This was g composed with f. I got a 3x plus 9 up here I got a 1 minus 4x over here. And the domain is what now? The domain is what? The set of all acceptable inputs. And the set of all acceptable inputs is the set of all real numbers with one exception, or two exceptions. X cannot equal 1/4. X cannot equal 3/2. Cool. Oops. Cool. So here's our answer right there. Now if you wanted to write this domain in interval notation, remember you have to go in order of the number line. Negative infinity is over here, infinity is over here. 1/4 is right about here, 3/2 is a little bit bigger. You get these two holes because you can't use those. And so what is the interval? It's, well, you've got from negative infinity coming up to 1/4, but not including 1/4. Union, you have another interval in here. Start at 1/4, go to 3/2 without including either one. That's why we have the rounded parentheses here. And then union again, you start on the other side of 3/2 and go to infinity. So that's how you would write it properly in the interval notation. I think I'll throw a PS on here, just because it's valuable to know these kinds of things. Being able to massage your little formulas and stuff. I kind of massaged it already when I said I didn't want to. Remember, I didn't want to have this, a negative 4x plus 1. Negatives in front make me nervous, make me anxious. So it's like, okay, I got a negative 4x there. Boo on that. So instead of negative 4x plus 1, I could switch it around, right? 1 minus 4x. Here's something else you could do. Or even, and I do this just in case you see this happen somewhere. You could, there's the 3x plus 9 on top. Now on the bottom, since you have that negative 4x, you could actually pull a negative 1 out right here, and this would become a 4x minus 1, right? So it's like I'm undistributing, if you will. I'm taking out a common factor of negative 1 from this and from this. It leaves me with a 4x and a minus 1. Because, again, if I distribute, I'll have a negative 4x plus 1, right? So that's, you could pull out the negative like that. And then, to divide by a negative 1 is the same thing as to multiply by a negative 1, so you could just put a negative out front like this. So that's another cool form. So that form's okay with me. That form's okay with me. That form makes me, I wouldn't call that, yeah, I would. That's no good. You never want to have negatives in your denominators. You would never ever write 3 over negative 4. You would always write negative 3/4, right? Always. So this is kind of the same thing. Leading with negatives is just, unless it's absolutely necessary, usually you try to manipulate it so you're not leading with a negative. So again, two choices for you here. That choice, which is fine. This choice, which is even better. Alrighty. That's our composition of functions.